Now we have an expression for the electric field intensity at a point on the axis of a small dipole of dipole moment P. What was that? Just recall the expression. Just recall the expression. Electric field intensity at a point on the axis of a dipole, at a point on the axis of a small dipole of dipole moment P. The expression was 1 by 4 pi epsilon naught 2p divided by x cube. Was that? And in vector form, this was the expression. If this is minus q, this is plus q, and this is the point at a distance x, then we know P is equal to Q into 2L. If this length is 2L, then field at P was 1 by 4 pi epsilon 0 2p by x cube, and this was the direction of P. Now, have we calculated the magnetic field on the axis of a circular coil? Have we calculated that? Magnetic field at a point on the axis of a coil, rather circular coil carrying current I. What was that expression? mu naught I a square by 2 into a square plus x square to the power 3 by 2. Was it? Circular loop, this is the center, then this was the axis, and this is the distance of the field point from the axis. The radius of the circular coil is A, and I current is flowing through the coil. Then at a distance x on the axis of the loop, magnetic field B is equal to mu naught I by mu naught I a square divided by 2 into a square plus x square to the power 3 by 2. Now, this can be written as mu naught by 4 pi. Okay. 2 pi a square into I divided by a square plus x square to the power 3 by 2. Is it? This 2 pi, 4 pi cancels 2 you get, and I into a square. Okay? Now, we may write this as mu naught by 4 pi 2IA, where A is the area of the loop, which is pi into a square, and since x is at a far point, therefore we can say that x is much greater than a. So a square plus x square is nearly equal to x square, and from that we get this as mu naught by 4 by 2IA by x cube. Now, if we replace IA by the term M, which is magnetic dipole moment, then we can write this as mu naught by 4 pi 2m by x cube. The similar expression. Now, the results obtained can be shown to apply to any planar loop. It is not for only the circular loop. It can be applied for any planar loop. Therefore, a planar current loop is equivalent to a magnetic dipole of dipole moment M is equal to I into A, where I is the current and A is the area of the loop. And this is analogous to electric dipole moment P. Right? However, a fundamental difference. There is a fundamental difference. What is that? That is, electric dipole is made up of two elementary units. The charge. One is positive charge, another is negative charge. And that is called electric monopole. But in magnetic or in magnetic case, in magnetic field. What is that? In magnetism, a magnetic dipole. That is, what is magnetic dipole? A current loop. Magnetic dipole means, we mean here a current loop is the most elementary element. The equivalent of electric charge, that is electric monopole. Are they here? We know there is an electric monopole, but is there any magnetic monopole? Right? This is the main difference between electric and magnetic. Electricity and magnetism, there is a fundamental difference. In electrostatics or electricity, you get electric monopole, that is charge, but in magnetism, you do not have any magnetic monopole. You do not see till now. Till now, there is no magnetic monopole. Clear? Magnetic monopole are not known to exist till now. Now we have shown that a current loop produces a magnetic field and behaves like a magnetic dipole. A current loop in magnetic field experiences a torque. Already we have discussed that, and the expression of torque we have deduced. Thus, you can say that a loop is like a magnetic needle. We have already told that from this discussion that a current loop, any type of, it may be circular, may be rectangular, may be any other loop, produces a magnetic field, right? A current loop produces a magnetic field and behaves like a magnetic dipole at large distances, and is subject to torque like a magnetic needle. This led Ampere to suggest that all magnetism is due to circulating current. No magnetic monopoles have been seen so far. However, elementary particles like electron, proton also carry an intrinsic magnetic moment. We are going to discuss the magnetic moment of an electron. Later we will discuss. We deduce two expressions. One is, if a loop, current carrying loop is placed on a uniform magnetic field, then it will experience a torque, and that torque is M cross V. And again, we have discussed another result. We have already deduced that magnetic field on an axial point of a current carrying circular loop, which is 2 mu naught by 4 pi 2 m by x cube at a far point from the loop. Now just we compare these two results. One is this, another is this. Two are electric field, and these two are in similar curve, and these two also are in similar curve. But in electrostatic field, we have told this as dipole moment, and dipole, which consists of a similar or same amount of positive and negative charge placed separated by a small distance, and that is electric dipole. Here also P is electric dipole moment. Now comparing these two, we can say this as magnetic dipole moment, this is magnetic dipole moment, right? Comparing these two, we can say that this is magnetic dipole moment. Magnetic dipole moment of what? Of a magnetic dipole. Now, is there any magnetic dipole here? No, there is a current carrying loop. So we can say that a current carrying loop can be compared with a magnetic dipole, or you can say a current carrying loop is a magnetic dipole. That means that is a magnet. A current carrying loop is a magnet, and that current carrying loop has two poles. One is north pole, another is south pole. In the side from which you have seen that current is flowing in anti-clockwise direction, that side will be north pole, and the side from which you you consider the current is in the clockwise direction, in that side there will be a south pole. So a loop is a magnet of two poles. One is north pole, another is south pole. Though as such there is no magnet, but I have a current carrying loop, and that loop behaves like a magnetic needle or magnetic dipole, just as north pole and south pole separated by a small distance.